Yo, welcome back. All right, we get into some good stuff now. All right, now we're going to start to talk about some shortcut rules for finding the derivatives of various types of functions. So let's start with the first one. It says derivative of a constant function is zero. All right, and then we can bust out some crazy fancy math symbols, basically saying, hey, if C is an element of the set of the reals, if you take the derivative of C, this is command notation, you get zero. You might see it in regular prime notation. If f of x equals C, then the derivative at any x is going to be zero. Now, before we do the proof of that, that should actually make sense to you if you think about it. Because if we came over and we graphed a constant function, right? What does any constant function look like, right? Hopefully you would say, oh, it's a horizontal line. So if I was to graph, say here, call this f of x equals c, where I'm depicting c to be positive, but it doesn't have to be. Think about it. No matter what x value you pick, if you draw in a tangent line at that x value, and it doesn't matter where you pick it, what is the slope of any one of these tangent lines going to be? Zero. So we remember, okay, easy enough. The derivative of a constant is zero. So pretty easy to see graphically. But how would we prove it? Well, everything goes back to the definition of the derivative. Everything. All right. So if I wanted to prove that, I would have to bust it out. So let's do that. Let's do f prime of x equals the limit as h goes to zero, f of x plus h minus f of x all over h, right? We've done a decent amount of time, spent a decent amount of time studying this. So now how do I do this? Well, I start with f of x plus h. So what is, and let's make this a little thinner, right? What is f of x plus h? Well, I have to put x plus h in the function f where I see an x. Well, there is no x, right? The function is a constant. That means f of 1 is that constant. F of 2 is that constant. F of the milkman is that constant. F of anything is that constant. So f of x plus h, that's just going to be c. Okay? And then we got minus. And now I have to do f of x, right? So f of x, well, duh, f of x, that's also c. I don't know why I'm saying duh. All right, and then all over h. So now you might think at first glance like, oh, you're going to get an indeterminate form, but we're not going to do the limit yet. So let's simplify. So I would get the limit as h goes to zero of 0 divided by h. So now what is 0 divided by h? In other words, don't do the limit yet. Just do 0 divided by h. Well, as long as h isn't 0, which it's not, it's going to zero, then 0 divided by h is going to equal 0, right? 0 divided by any real number other than 0 is going to be 0. So I can simplify this as the limit of 0 as h goes to 0. And then what do you know about the limit of a constant? It's the constant itself. So that is the proof that f prime of x would be 0 here. If I wanted to bust out command notation, the derivative with respect to x of some constant c, it's just going to be 0. All right. You'll never have to do that proof ever again. We just show you that so we can feel good about ourselves when we go to sleep at night. You just have to remember the derivative of a constant is 0, and you can even think of the graph, which should make sense. All right. Power rule for derivatives. This is another really, really good one. Okay. So let's look at this as if we're reading a math textbook. It says if n is a real number, then the derivative with respect to x of x to the n is going to equal this, n x to the n minus 1. So this is command notation. This is prime notation, right? It's the same thing. The derivative of x to the n is n x to the n minus 1. So it looks like you take that power, you throw it down in front, make it a multiplier, and then write x and then subtract 1 from the power. So that's a shortcut rule for taking the derivative of a power function. So now before I get into the proof, just so you understand what this is saying, if I had like f of x and it was x to the 50th power, well, according to this theorem or this rule I just gave you, the slope producing machine for this, the derivative, simply can be done by, all right, the n goes in front, that's like my n, so 50x and then subtract 1, right? So it's a 49 there. So you got to be like, well, that's pretty amazing, because if I asked you to find the derivative of this using the definition of derivative, you'd be pretty miserable, all right? Because you'd have to do, I can't speak, you have to do x plus h to the 50th power, right? That'd ruin your whole day. All right, so what's the proof of this look like? And I don't want to spend, honestly, too much time on the proof, but I will start it. So this is only a proof for when n is an element of z, so an integer, right? It actually works when n is any real number, but the proof is a little bananas. So we'll just look at the proof for when the exponent is actually an integer. So here we go. So the derivative with respect to x, so whether I'm command notation or prime notation, I start with this. Guys, what is that? You should be like, oh, this right here, that's the definition of the derivative. That's where you always start with. So now to do f of x plus h, if my function's x to the n, then f of x plus h would be x plus h to the n, then minus x to the n over h. Now, normally with these power functions, right, we would multiply this out, because if I chuck 0 in for h right now, I get an indeterminate form, right? So if it was like x plus h squared, you'd multiply it out. If it was x plus h cubed, you multiply it out. And squared and cubed aren't so bad. Well, when it's the 50th, it would be bad. So, but how am I going to do that, though? It's not squared, it's not cubed. How do I expand this binomial? Well, you have to know the binomial expansion. So what you see in red here gets expanded into what you see in red here. So at one point in your math life, before calculus, you probably learned the binomial expansion. All right, so if you remember, this is red, n choose 0, x to the n, h to the 0, plus n choose 1, so on and so forth. Now, what is n choose 0? Well, it turns out that that's just 1. N choose 1 is just going to be n, and then n choose 2 would follow kind of this manner, and so on and so forth. So at the end of the day, this is just going to be a coefficient. So it actually doesn't even matter if you're not really sure where the heck that coefficient's coming from. You can make up a number. It's not going to matter, because you're going to see this proof's going to work out the same. What do I mean? Well, first off, when you expand all of this, right, pretty obvious that you're at least going to have an x to the n term in there, right? Well, guess what? It's going to cancel or sum to 0 with the x to the n over here. So I wipe those out. So now what does that mean? That means everything left has an h in it. So I can choose to factor out the h up top and cross it out on the bottom, or I can choose the, we like to say, give out the lemonade. This h divides every single one of these terms. So when this h goes into that term, there's not going to be an h there anymore. You're just going to be left with n x to the n minus 1. That's what you see right there. Now, all of the other terms, guys, are going to have an h in it. This will have one h, the next term will have an h squared, and so on and so forth. Well, remember what you're doing here. You're taking the limit as h goes to 0. So all of these other terms will be multiplied by 0. So they are gonzo. So you're just left with this. So you're like, holy cow. That's the proof that the derivative of x to the n is in fact just n x to the n minus 1. And again, that's just a proof when n is an integer, but it works when n is anything. It could be a fraction. It could be an irrational number. It doesn't matter. It always works. The proof is just a little bananas, so we're not going to do it. All right, so before we get to practicing that cool rule, I just want to show you one more rule here. All right, so let C be a constant. If f is differentiable at x, then so is the constant times that function. So if you have a differentiable function and you multiply it by a constant, you still have a differentiable function. So now look at what this rule says. It basically says if you're taking the derivative of a constant times a function, just take the derivative of the function the way you normally do and multiply by a constant. You can almost think of this as a constant can be moved through a derivative, much like a constant can be moved through a, what do you think? A limit, right? So the proof of this is really not too bad here, so we'll do it, right? So if I want to do the derivative with respect to x of some constant times f of x, right? So I'm kind of using command notation here. It would be the limit as h goes to 0. So now remember that first part of it is that f of x plus h. It's your function that you're trying to take the derivative of, evaluated at x plus h. So that means putting an x plus h in here. So it would be c times f of x plus h minus the function. So that's c times f of x, because that's what I'm doing now, all over h. So now notice, what can I do with that c up top? That c can be factored out. And c is a constant, and you've already learned that constants can be moved through limits. So I can write this as c times the limit as h goes to 0 of f of x plus h minus f of x all over h. And you're like, oh, look at that. What is this? This is the definition of the derivative, right? That is f prime of x, or if I'm using command notation, d dx of f of x. So that means that this is equal to c times d dx of f of x. If I wanted to do c times f prime of x, I could. All right. Long story short, a constant can be moved through a derivative, and that should seem pretty intuitive since you can move constants through a limit. All right, so let's get to the good stuff. So it says, using the appropriate notation, find the derivative with respect to x. So you'll see I kind of jump around with the different notations here. So you have f of x equals 8, so I'm going to use prime notation for this first row. So what would the derivative be? All right, what do you think it would be? Hopefully you're saying 0. Why? Because this is a constant function, and the derivative of a constant is 0. If I was to graph this, it'd be a horizontal line, and the slope's going to be 0 at any point x. Okay? All right, now what about this guy here? How would I take the derivative of that? Well, let's be careful now, all right? A couple ways to think about this. Um, if we want to use the rules that I just gave you, right, f prime of x here, it would be the constant times the derivative of x. Now, I can think of x as x to the 1. So using that power rule, it would be 1x, subtract 1 from that, to the 0, right? And so x to the 0 is going to be 1. I end up getting 6 here. You should never do this problem that way. Right? I almost should have made this a separate rule up above, right? You know what the graph of 6x looks like. 6x is going to be a line that goes through the origin and has a slope of what? It has a slope of 6. So no matter where you draw in a tangent line, since this thing is linear, it doesn't matter. The slopes will always be 6. So if I tell you what's the derivative of 6x, you're going to tell me right off the get-go, that's 6. So maybe even make a note, maybe the key here. If I said f of x was m times x, what would its derivative be, right? It would just be m, right? So it's using the rules we did above, but maybe it's kind of streamlining it and developing our own rule. All right, here we go. Maybe I should have gave you this example first. This is straight up power rule. What's the derivative of x to the 5th? Well, if I'm using the power rule, it says bring the 5 down, make it a multiplier, 5 times x, then subtract 1 from that. So I'll show the work there, but you don't have to. It's just 5x to the 4th. So that took us about 30 seconds to get the slope producing machine for x to the 5th. If I asked you to do that using the definition of the derivative, it's taking you more than 30 seconds. So you are welcome. I know you're very excited about that rule. All right, let's do this next line here. All right, and let me change the color here to make it even more exciting. So now this is command notation. So this means take the derivative of negative 11 with respect to x. So the way I would write this is I'd show the derivative with respect to x of negative 11, sort of a constant, it's just 0. That's how you write it. Don't you dare write anything crazy like that. That doesn't make any sense. That's like a half a radical, right? That d dx of what? It always has to be d dx of something equals something. All right, so this is command notation. So just pay attention when you have that. All right, here, d dx of this. What is the derivative with respect to x of 7x to the 5? Again, I can kind of take my time here and watch what I'm going to do. Instead of rewriting the problem, I'm just going to go whoop, just like that, and say, all right, this is equal to 7 times d dx of x to the 5th, because a constant can be moved through a derivative. Now, how do I do the derivative with respect to x of x to the 5th? Well, that's the power rule. That's 5x to the 4th. What do I do with this 7 and this 5? I multiply, so I get 35x to the 4th. So this is like good for note flow, but you ain't writing these two steps when you're asked to do this problem. You are going to go straight from here to here, right? The derivative of 7x to the 5th, oh yeah, that's going to be 5 times 7, that's 35x to the 4th. And you're going to get right at it. All right, again, this is command notation, ddx of. Here's another command notation. Now, this might spook you out because there's divided by there, but it might be a good idea for you to think of this. I'll rewrite it, ddx of, right, 1/4 times x cubed, because now I have put it in a form that I can relate back to what we just studied. So this is just constant times a function. So again, for note flow, I'll pull the constant out and get the derivative with respect to x of x cubed. And now to do this, I do my new power rule. So it's going to be, here's my 1/4. This is just going to be bring the 3 down, x, subtract 1 from that. Okay, what can I do with the 1/4 and the 3? I can multiply it and get 3/4 x squared. You are not required to show all these steps. You literally can say, all right, this is 1/4 times x cubed. So I know that the answer is going to be 1/4 times 3 or 3/4 x squared. Okay. Command notation, command notation. All right. Let's do the next couple of problems. Let's do 7. All right, so now I have options here for notation. I could write y prime, or I can use the notation I haven't used it today, which is Leibniz notation, that's what I'm going to do. So now I have y equals 5 squared. I'm going to use the notation dy dx. If you wanted to use y prime, you could, but maybe for note flow, just follow my lead. So what is the derivative? Notice this isn't command notation, guys. This isn't d dx of. This is dy dx. That's the symbol for the derivative. What would it be here? Right? Maybe pause the video and see if you can do these three. When you come back, hopefully you said 0 here and you didn't do anything silly like 2 times 5 to the 1. You're like, oh, that's what I did. Well, hopefully you didn't, because what is 5 squared, guys? It's just 25, right? At the end of the day, this is a constant. This is not a function of x. It's a constant. And what is the derivative of a constant? It's 0. So now you come to this guy and you're like, wait a minute, how, I paused the video and I looked at this and you didn't show me how to do radicals. No, I didn't, but I did give you a power rule, and you did learn back in the day that you can rewrite radical x as x to the 1/2. So this isn't the derivative, this is y. Maybe I'll even emphasize. All I did was rewrite y as x to the 1/2. So now I can take the derivative using the power rule, which is, all right, bring that exponent down, 1/2, that's the multiplier, x to the, I have to subtract 1 from that. Now, when I'm thinking in my head subtracting 1, I'm not going to write -1. In my head, I'm going to write minus a good version of 1, which in this case, since the denominator is 2, I would think subtract 2 over 2. If the denominator was 3, I would think subtract 3 over 3. If the denominator was 7, you guessed it, I would think subtract 7 over 7. And so now what do I get? I get 1/2 x to the 1/2 minus 2/2 is negative 1/2. And that is a fine answer, by the way, but you may not see that if it's a multiple choice. So what could you do? Properties of negative exponents, right? There's this 2 on the bottom. I can chuck this down here, and now I rewrite it as a positive exponent. Okay? You might not see that. You're like, well, why? Well, because x to the 1/2 can be written as radical x, right? So you might see the answer is 1 over 2 radical x. I would ask you, honestly, there's going to be a couple of derivatives I want you to memorize. This is one of them. So if I say memorize the derivative of y equals radical x, you'd be like, all right, I got it. It's 1 over 2 radical x. Okay? Again, don't lose sight of what you're finding. You're finding the slope producing machine for this function, and we're doing it real quickly. Okay? Let's take a look at 9. Again, 9 seems a little wacky at first, but you're like, you know what? Let me rewrite this. All right? I can write this as x to what power? Pause the video, see if you know what it is. Right? Hopefully you said negative 1/3. And understand that there's two things going on here. The negative has nothing to do with the radical. Nothing. The negative has to do with this fact that it's in the basement. All right. The 1/3 has to do with the radical, which has an index of 3. Like if I rewrote this, it'd be 1 over x to the positive 1/3. And if I want to move that up, then I just use my property of negative exponents. So keep those things clear in your head. That negative exponents and radicals, they're separate concepts there. Radicals are fractional exponents. Negatives are basically 1 over deals. All right, that didn't make much sense, but hopefully you get what I'm talking about. All right, so anyway, all I did was rewrite y. That's it. I rewrote y. So now dy dx, what would it be? Well, I'm going to do the power rule. So bring down the exponent, negative 1/3, x to the, what do? I have to subtract 1 from that. And for note flow, I'm going to show the work today, but normally you're not showing this work. So negative 1 over 3 minus 1, I'd rather think of it as 3 over 3. Negative 1 over 3 minus 3 over 3 is going to be negative 4 over 3. And I'm going to leave that as the answer. If I wanted to write that as the cube root of x to the 4th power and then chuck it in the basement, I could, but I don't feel like it. So I'm going to leave it that way. All right, let's go to the next. Maybe we'll go back to prime notation here. So g of x equals x to the negative 4. Okay, I don't need to rewrite anything there. So I'm going to go right to g prime of x, power rule, bring that down, negative 4x to subtract 1. What is it? Say it out loud in your head. You said negative 3, you messed up, right? Because on a number line, if you are at if you were at -4 and you subtract 1, you're going that way, right? You're going to -5. So just be careful with the negative exponents, right? Not that you have to do this, but it might be a multiple choice. You might see that, right? Again, property of negative exponents. What about over here? G prime of x. I don't need to rewrite anything. In fact, I'm going to get right after this. I have -5x and -3 power rule. -3 times -5, that's positive 15. I'm just going to go right to it. X to the subtract 1 from that, -4. All right, call it a day. All right, take a look at this guy, G prime of x. All right, you're going to have, maybe for note flow, I'll show it. You have that 2, and then times, bring this down, 3/2 x to the, again, for note flow, I'll show me subtracting 1, subtracting 2 over 2. All right, but quite honestly, you really should be just being like, all right, 3/2 times 2, yeah, I know the 2's are canceling, right? So I'm going to get 3x, and then 3/2 minus 2/2, that's 1/2. Again, if it's multiple choice, maybe you see that. But you don't have to do that type of stuff unless it asks you to, or if it's multiple choice. Okay, so that's some good notation practice, and that's some good practice of those rules we just did. So now there's one other rule, really two other rules that I want us to look at today, which is, all right, well, what happens if you want to take the derivative of a sum? Well, good news for you, much like with limits, right? The derivative of a sum is just the sum of the derivatives. So what does that mean? It means if you're taking the derivative of a sum of two functions, just take the derivative of each function individually and add them. Now, I'm not going to spend the time and go over the proof, but here's the proof right here. It's pretty easy. You can pause the video and look at it. This is me evaluating that sum function at x plus h. This is me subtracting the sum function, right? And then over h. So this is basically the definition of the derivative being applied to this function. And then all I do from here to here is I just use what I know about math to kind of split up the fractions and rearrange terms. All right, and then use a property that the limit of a sum is the sum of the limits. And you can see now, you're like, oh, take a look at this. That's the definition of the derivative for f, and that's the definition of the derivative for g. Now, turns out that limit of a sum of the limits. Well, guess what? The limit of a difference is the difference of the limits. So the proof of this guy is going to look exactly the same, except wherever you see those red plus signs, change them with a minus sign. Okay? All right, so now that's pretty good. So now a little note here. It says derivatives don't behave as nicely as limits. For example, the derivative of a product is absolutely not the product of the derivatives, right? So remember, with limits, you could be like limit of a product, product of limits, limit of quotient, quotient limits. You had all that stuff. Limits worked awesome. The buck stops with sum and difference with derivatives. So we're not doing it today, but if I asked you to do the derivative of a product, you couldn't simply take the derivative of the individual functions and multiply them. It's a little bit more complicated. But we'll get to that when we get to that. All right, so here we go. Let's use appropriate notation to find the derivative with respect to x. So you can see we got sums and differences here. So if I want to find, we'll call it f prime of x, right? I don't need to write, d dx, d dx. I don't have to. I'm just going to do it, right? I know the derivative of sum is sum of the derivatives, so I'm basically going to take the derivative of each term. So what's the derivative of 3x to the fourth? Well, using the power rule, it would be 12x cubed, right? Bring the 4 down, multiply. 4 times 3 is 12, and then subtract 1. Same deal here. Bring the 3 down, multiply by the 5, then subtract 1. So that would be plus 15x squared. Now, what do you do here? This is that one I said I probably should have gave you a separate rule for. Right? Who remembers what the derivative of just negative 2x would be? Hopefully you're saying it's just negative 2, right? It's basically a line, goes through the origin, has a slope of negative 2. So the slope of the tangent line at any point is negative 2. If you didn't like that, then technically you can be like negative 2 times 1x to the 0. So it's like you're using the power rule on that, right? And x to the 0 is 1. I guess you could do it that way too. And then what's the derivative of plus 6? Well, that's a constant, so the derivative is just 0. So now, oh, wowzer. So look what I did there. Derivative sum of derivatives, derivative difference, difference of derivatives. It took me about 30 seconds to find the slope-producing machine for this function. Think about if you would have to do that using the definition of the derivative, right? That'd ruin your whole Saturday night. All right, let's take a look at this guy. Let's just follow lead with the prime notation. Although, you know what? Maybe I'll go crazy. Let's go Leibniz notation, df dx, okay? And then here I go. I mean, why? It's like a Band-Aid, man, all in one shot. Pause the video, honestly. Don't watch me do this, all right? Pause the video, do it yourself. All right, welcome back. Hopefully you got this. Negative 14 x to the sixth plus 15x to the, don't fall for the trap, subtract 1 from that, negative 4, plus 24x to the 1 minus 4 plus 0. Bam, done. Call it a day. Move on to the next problem. All right. Hopefully that's good. All right. What about 3 and 4 here? So 3 and 4 now we have command notation. So again, don't be that person that writes this. That doesn't make any sense. It always has to be d dx of something. Has to be that. So you already have it right here. So I'm not rewriting it all, right? So I'm just going to do that. Say, all right, all of this equals. Here I go. Again, it's just one big, like, sum rule and power rule fest here. 1/3 times x, that's going to be 1x to the, subtract 3 over 3 from that. So 1 over 3 minus 3 over 3, negative 2 over 3. Okay? Minus 2/5 times 5. The 5s would cancel. So minus 2x to the, subtract 5 over 5 from that. That's minus 3 over 5. All right? Minus 16x to the, subtract 1, negative 3, plus 12 plus 0. Notice I didn't show as much work on that one right there, right? I didn't show you, although I guess I'm showing you now, negative 5 times 2/5, and oh, you can cross out the 5s, right? I just went right to it, and that's the idea. That's what we want you to be able to do. All right, this guy over here, command notation. Doesn't look like there's much that I have to rewrite, although I might want to view or think of x to the 6 over 12 as 1/12 x to the 6th, right? So in my head, that's kind of how I'm thinking that's going to go. All right, so here we go. Again, it's command notation. It's ddx of, so it just equals. Okay, so all of this equals. Derivative of 25, 0. Derivative of this, 3018, that's going to be 48x, subtract 1, squared. Negative a half times negative 4, that's going to be positive 2. X to the, subtract 2 over 2 to that, from that. It's going to be negative 3 over 2. All right, plus, what's 2 sevenths times 6? You're like, oh, I have no idea. Well, what's 2 times 6? 12. All right, divided by 7. So you're going to get 12 over 7. Let's stop panicking, for God's sake, right? 6 times 2 over 7, 12 over 7, x to the, subtract 1. 2 over 7 minus 7 over 7, negative 5 over 7. Easy breezy. All right, plus, and then here, I rewrote it in my head. This is my brain right here. So when I do the power rule, 6 times a 12th is 6/12, otherwise known as a half, x to the 5th power. And my God, look how easy it is to get slow producing machines now, derivatives, using just a few rules that we gave you. All right. That's pretty awesome. All right. So the rest of these notes talk about higher derivative notation. We're not going to discuss that right now, but really there's more than the first derivative, right? Like this is the first derivative. If I wanted to get the second derivative, all I would do is just take the derivative of the first derivative. I'd keep doing it. But we're not ready to do that just yet. All right, so hopefully that helps. Be good.